Good day, students. I welcome you to your favorite YouTube channel, Physics for Everybody. Today we'll be solving February-March 2024 Physics 0625 Paper 6 Variant 2. Without delay, let's go. Question number 1. A student determines the mass of a meter roll by balancing method. He's using this apparatus shown in figure 1.1. So this is the apparatus and this is the top view of the load. Okay, so if you view this load from the top, this is what you see. Now you have to determine the distance of the center of the load from the zero end of the roller as shown in figure 1.2. Figure 1.2 is not to scale. So how do you measure the distance from this center to the zero mark? So viewing it from the top, this is what you see. How do you determine this center mark here? So the smartest thing to do is to consider the distance to the left and the distance to the right this way. You see, there's equal distances. Let us see the number of divisions we have. From here, we count 1, 2, 3, 4, 5, 6, 7, 8 to the right. Let's count how many we get to the left. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that means it is at the center of these two marks, at the center of 26 and 30. What do you have at the center of 26 and 30? 26 plus 30 divided by 2. That will be 56 divided by 2. And that will be 28 centimeters. And that's the center mark. So that's what we have here, 28 centimeters. But because this is practical and the meter rule is calibrated to the nearest 0.1 centimeter, okay? If this is 30, this is 31, this smaller division will be 30.1. So your meter rule is calibrated to the nearest 0.1 centimeter. Therefore, the correct answer here would not be 28. The correct answer here would be 28.0. 28.0 centimeters. So that is how you put the calibration of your measuring instrument into consideration in everything you do. Let's go to the next exam. The next question, please. So please, this is the best video you can find on paper 6. Share it with your friends. Let's go. The students adjust the position of the meter ruler on the pivot until the meter ruler is as near as possible to being balanced. Describe a technique for ensuring that the ruler is as near as possible to being balanced. How do you ensure the meter ruler is as near as possible to being balanced? I've put it here. So what you do is you continue adjusting the position of the meter ruler on the balance point until it oscillates slightly, okay, or until it stops slightly. That is what you do to ensure it's as balanced as possible. Okay, good. The next question. The student finds that the ruler is as near as possible to being balanced when the pivot is at 47.6 centimeters mark rather. Calculate the distance A of the center of the load from the 50 centimeters mark as shown in figure 1.1. Use your value of D from A and the equation A equals to 50.0 minus D. What is D? Look at the diagram. D is distance from the center of the load to the pivot. And what's the value of D? We have the value of D as 28.0. So you just put that here, okay? 50 minus 28.0, 50.0 minus 28.0, that will give you 22.0 centimeters. Don't forget the number of decimal place, okay? You must write it to the nearest to one decimal place, which is 22.0. If you are written 22, that will be wrong. The next question, calculate the distance B of the center of the load from the pivot as shown in figure 1.1. Use your value of D from A and the equation B equals to position of pivot minus D. What's the position of pivot? We were told that the position of pivot is, look at the position of pivot. Position of pivot is what? We were told that the position of pivot is at the 47.6 cm mark. So if the pivot is at the 47.6 cm mark as stated in the question, what will you do with that? You see, the pivot is at the 47.6 cm mark. Okay, so you put that into consideration. Position of pivot minus D. What is D? D is 28.0. So you just do 47.6 minus 28.0. That's what you do here. And you get the answer to that. 47.6 minus 28.0, you get 19.6 cm. That's the value of B. So that's it. Very easy. Now let's go to question C. The student moves the load so that its center is above the 5.0 cm mark and balances the meter ruler. He repeats this procedure for the load at 10 cm mark, 15 cm mark, 20 cm mark and 25 cm mark. His results are shown in table 1.1. So this is the table, these are the results the student got. Plot a graph of A in centimeters, okay, in the y-axis against B in centimeters on the x-axis. Use the values in table 1.1. You do not need to start both axes at the origin. Since you are not starting both axes at the origin, what would you do? Now let's have a look at this together. Since you are not starting both axes at the origin, the value of A go from 25 to 45. So picking a reasonable scale, don't forget that you are putting A on the y-axis. So the first thing you do is you draw your axis, a vertical line, and you label it A axis, okay? A in centimeters. While the horizontal line, which you draw this way, this is your B axis, so you label it B in centimeters. Now let us pick this B axis, okay? As per your graph, axis ends you 1 mark, your scale ends you 1 mark, all the 5 points plotted correctly, that will earn you 1 mark. Then your line of best fit ends you 1 mark. So we've gotten the 1 mark for the axis. Let's pick a reasonable scale for our graph. Since we are not starting both axes from the origin, what will you do? Now let's see, on the x-axis, our values range from 25 to 45. So let's just slot that here. Our values range from 25 to 45. So if we take this as 25.0, if we take this as 25.0, 25.0, and we take this as 30, 35, 40, 45. Okay, that will be 25 to 45. Yes, that's going to work. That will capture 25 to 45. So let's put that here, 25, 30.0, 35.0, 40.0, 45.0. So what about the values on the B axis? Let us pick our values on the B axis. Our values on the B axis range from 22.5 to 40.5. 40.5. So if you take this as 40, okay, this can be 20, this can be 0. Our values range from 22.5 to 40.5. So 22.5 will be around here. Our values will now range within this. No, that's not good. So let me put 20 here. Let me put 20 here. Yeah, so if this is 20, the middle is 30. Yes, then our values can range from 22.5 to 30. So let's see if this is 20, this is 25, 30, 35, 40. So 22.5 should be around here. 22.5 to 40 will be around here. So that's how I pick my axis. Okay, that's how I pick my scale. I consider the range of values and I try to imagine how that range of values will be on the graph. If it's too small, initially what I had was like this, within this range, which is too small. Okay, so I had to expand my scale till I got a wide range of values. So that wide range of values will allow you to plot a very good graph. So I did that here. I used that scale 20, 25, 30, 35, 40. Okay, that means that means I started my x-axis from 15, where I started my y-axis from 25. So you make sure you label that correctly and you put those values there. Label your a-axis, label your b-axis. Now the point, you plot your points correctly. How do you plot your points correctly? Look at the value of A. When A was 45, B was 40.5. So we go, when A was 45, you make sure the value of B is 40.5. Let's zoom in so I can have a broader view of our values of B. So if this is 40, if this is 35, 36, 37, 38, 39, 40. You see that two divisions make one unit. This is 41, 42. So if this is 41, then between 40 and 41, I will have 40.5. That makes this middle line 40.5. That's why when I wanted to plot the point for 40.5, I picked the middle of that line. I picked the middle line. Sorry. I picked this middle line. This is 40.5. Yeah, that's it. So that's how you plot your points correctly. That is how you plot your points correctly. You consider the values you have. If this is 40.5, yes, so if this is 35, this is 40. 1 point after 40 will be 40.5 because 2 points represent 41, okay? 2 points represent 1 unit. Yeah, so that's it. I believe that is clearly noted. So what about this when A is 40, B is 35.2? Let's go. When A is 40, our B will be 35.2. So let's zoom into the value of B again and have a look. If this is 35, this is 36, 37. Since this is 36 and this is 35, between 35 and 36, we have 35.5. Now, if this middle line is 35.5 and this thick line is 35, between 35 and 35.5, we have 35.25, which is the closest approximate value of 35.2. That's why I picked this middle line as my 35.2. Okay, that's why 35.2 was placed in this middle, 35.2. So you have to do that for all the other points. Okay, be very careful when selecting your points. Please download this question paper and practice with me. As you are watching the video, start drawing this graph. Draw this graph with me, draw this line with me, and draw your line of best fit with me. Okay, so look at the way I pick my line of best fit. How many points do I have to the left? 1, 2. How many points do you have to the right? 1, 2, 3. That is still a reasonable line of best fit. Okay, just be very careful when doing your line of best fit and make sure you use a ruler. The reason why my line is curved is because I didn't use a ruler. If you use a ruler, you should get a perfectly straight line that you can use to do your slope. The next one says determine the gradient G of the graph. Show clearly on the graph how you obtain necessary information. How do you do the gradient of your graph? The first thing you do, you draw a big right angle triangle. Okay, you draw a big right angle triangle. Let me make my graph look straight because my line of best fit doesn't look straight. Okay, and that can confuse my students. So let me try to make it as straight as possible. It's very difficult to get a very straight line when you are not using the appropriate drawing instruments. But let's just assume, no, this is not a very good assumption. I wanted to assume my line is straight, but even the assumption is not good enough. So let me just try to get a very straight line of best fit. Okay, so we can still manage this. We have 3 points on the line. Let's assume this is a perfectly straight line. We have 1 point on the left, 1 point on the right, 3 points on the line. That's fine. And how do you do your gradient? You draw a big right angle triangle. Okay, everything must be done with your pencil. But let me just use color green so that you'll be able to see clearly that I'm drawing a big right angle triangle. You draw a big right angle triangle. Okay, it's your choice. You may choose to draw your big right angle triangle like this and use it to calculate your slope. Okay, it's your choice. In my own case, I've chosen to draw my big right angle triangle to cover the entire slope. Okay, so let me erase this line. Let me continue my green line. Make sure you use a ruler to draw this line. Okay, you don't have to trace this, you don't have to trace it on this red line. It's not necessary, okay, because you have already drawn the slope. Okay, so this green line, that's what I'm using to do my gradient. And what's the formula for gradient? Dy dx. Change in the value on y-axis divided by change in the values on the x-axis. Okay, and that is what we have done here. So let me just bring this out. This is how I get my gradient, okay? dy dx. What do I have on the y-axis? Here. So the graph I've drawn, the big triangle I've drawn, let's pick the value we have here. What value do we have here? We have 45. 45 minus, what value do I have down here? I have 25. So I'm doing 45 minus 25 divided by, what about on the x-axis? I pick this middle line, okay? So I have 40.5 here, 40.5 minus, what value do I have down here? This is 22.5, okay? Between 20 and 25, that's 22.5. So I pick my values from the big right angle triangle. This 22.5, this is 40.5. I was trying to trace this along the middle line, okay? I was trying to trace this along the middle line, and this middle line gave me, hold on. Sorry, I was trying to trace this along this thick line, yeah, not the middle line though. The thick line here, which is 40.5. So this thin line here is 40.5. That's what we got for 40.5, because two small boxes represent 1 unit. Therefore, um, one small box will represent 0.5 units. That's how I got 40.5. So I didn't, you don't necessarily have to pick the values on your table to do your slope, okay? Just draw a big right angle triangle and pick your values from the right angle triangle. Okay, so you take the difference, 45 minus 25, you get 20. 40.5 minus 20.5, you get 11. 20 divided by 11, I get 1.111. Fine, I write my values to three significant figures. Why? Because the maximum number of significant figures I have is 3. So I'll pick 3 significant figures. That's why I wrote 1.11. That's why I didn't write it to one significant figure as 1. No, I wrote 1.11. So that is a very good way to do this, and that's how I got 1.11. What's the SI unit? SI unit of A is centimeters. SI unit of B is centimeters. Centimeter per centimeter. That's nothing. Okay, so it has no SI unit. G has no SI unit. Let me return to this so that you can see the question clearly. The next question says, calculate the mass M of the meter ruler using the equation M equals to K over G minus 1. Since M equals to K over G minus 1, what's the value of K? We have given K as 25 gram. 25 over G is 1.11 minus 1. That will be 25 over 1.11 minus 1, you get 0.11. Divide 25 by 0.11, what will you get? If you divide 25 by 0.11, you will get 227 grams. That's how I got 227 grams as the value of M. Let's proceed. The accuracy of the results obtained by this procedure depends on the meter ruler without a load, balancing with the pivots at the 50 cm mark. Okay, now a student finds that this does not happen. She adds a small piece of modeling clay to one end of the meter ruler to correct it. Suggest if this is a suitable change to the experiment. Explain your answer. So the accuracy of these results depends on the meter ruler when it's not loaded. The meter ruler balancing exactly at the balance point, which is 50.0 cm. But if it does not balance at the 50.0 cm, if it's balancing somewhere close to it, be it here or here, all your answers will not be accurate. There will be little deviation. So a student did this experiment and found out that the balance point was a bit shifted to one side, probably here. Why would it be unwise for that student to add very tiny, small amount of clay here so that the balance point will eventually shift back to the 50 cm mark? Why would it be unwise? Because you must use a uniform meter ruler, okay, such that the mass will be uniform throughout the entire length of the meter ruler. Once you add small amount of clay here, this part is now heavier than the same quantity, okay? So it means it's no longer uniform. While this side has uniform mass, this side has bigger mass than this other side. Okay, and to be able to perform experiment on this kind of experiment, you must use a uniform meter ruler. So that's what we are stating here. Okay, so this is not a good modification to the experiment, because the meter ruler will become a non-uniform ruler. Okay, yeah, and the appropriate meter ruler must be uniform. Okay, so the appropriate meter ruler used for this experiment must be uniform. The appropriate meter ruler must be uniform. Okay, so let's proceed to the next part. That's the end of question number 1. We move straight to question number 2. A student investigates a circuit containing different combinations of 3 resistors. So there are 3 resistors here, and okay, all right. So on figure 1.1, I've answered this already. Let me just continue. On figure 1.1, draw a voltmeter connected to measure the potential difference PdV for terminals PQ. How do you measure the potential difference here? You draw a voltmeter in parallel to all of those, and that's how you measure the voltmeter there. Okay, and you may choose to draw your voltmeter this way. Your choice. Draw your voltmeter in parallel with all those components. That's how you get the voltage. Okay, the student measures the potential difference V for P and Q and measures the current I in the circuit. The meters are shown in figure 2.2 and figure 2.3. Read and record in the first line of table 2.1 the values of I shown on the meters in figure 2.2 and 2.3. What's the value of I here? Between 0 and 1, we have 10 division. That means each smaller division represents 0.1. If this is 3, the next one will be 3.1. So the voltage here is 3.1 volts. What about the current? Between 0 and 0.2, we have 10 division. That means each division represents 0.2 over 10. That will be 0.02. So that's how you know what each division represents. Here, the number of divisions here is 10. 10 divisions between 0 and 1. Okay, so 1 over 10, that gives you 0.1. So each tiny division is 0.1. That's why I wrote 3.1 here, because this tiny division is 0.1. But here we have 0.2. 0.2 divided by 10, I have 0.02. So each tiny division is 0.02 units. So let me now see. Between 0 and 0.2, I will have 0.1. So this line will be 0.1. Okay. So I just have one other tiny division after 0.1. So I'll just add 0.02 to the 0.1 and have 0.1 plus 0.02. I have 0.12 amperes. That's the current, 0.12. So please make sure you understand how to read the ammeter and voltmeter correctly. Make sure you know how to deduce what the smallest division is. That's it. So I have 3.1 volts, 0.12 amperes. Okay. And what's the next thing? The question says the student connects the resistors between terminals P and Q as shown in figure 2.4. She measures and records in table 2.1 the values of V and I. So the student modifies the circuit. Initially, the 3 resistors were in series. The student then disconnects this and connects the 3 resistors like this. Resistor 1, and then she connected 2 in parallel. Okay, so that's it. The student modifies the circuit. Okay, so between P and Q, she disconnected everything and reconnected those 3 resistors like this. Good. So now what they are asking you is that when she connects the 3 resistors like this, the values she got, she recorded them on the table. And that's what we have here as circuit B. You see, the current she got is 2.9. Sorry, the voltage she got is 2.9 volt, current she got is 0.22 amperes. Okay, what next? She went to see. The student connects the resistors between terminals P and Q as shown in figure 2.3. She measures and records in table 2.1 the values of V and I in this circuit. She now connected three of them in parallel between P and Q. That means she disconnected this series arrangement and connected the three resistors in parallel. Then she measures voltage again, measures current again, and records them on this table. That's what she puts here. The voltage, the current. Why did I put this here? Of course, the current asked me to do that. The question says, calculate and record in table 2.1 the resistance R for each circuit. Use the values of V and I from table 2.1 and the equation R equals to V over I. So I used the values of V and I here. I just did R equals to V over I. So I did that here. I divided V. For instance, how did I get this 26 ohms here? How did I get this 26 here? I just did R equals to the voltage, which is 3.1, divided by the current, which is 0.12. That will give me 26 ohms. I recorded my answer to two significant figure. Why? Because every other value is written to two significant figure. So that's it, and that's how I got my answer there. Alright, so I wipe this off since it's not necessary. Alright, let's continue. So I recorded everything on this column to two significant figure, okay? That's how I got all these values here, including this one to two significant figure. That's resistance. Alright, let's continue. So what else? Add units to the column headings in table 2.1. So if you look at the original question given to you, the table looks like this. Add units to the headings. Many students omit this thing. Many students don't see this question and they don't answer it. Just come here, put V as unit of volts, put A as unit of current in amperes, and put the symbol of ohm, omega, for resistance. That's it. Many students omit this thing and they don't answer this question. So little things like this makes you lose marks, okay? But if you do everything correctly, you get all your marks. The next part of the question, calculate a resistance RA. Use the value of R from this circuit A in your equation. How do you get RA? R over 3. R is the value of resistance in circuit A. Now, you must understand the question very well and everything you've done. What is the resistance from circuit A? Let me come back to this place. What's the resistance from circuit A? The resistance from circuit A is 26 ohms. Okay, so you must not get confused. We use that 26 in this calculation. So that's what we did here. R over 3, 26 over 3. That will give us 8.7 ohms. The next one, resistance RB. Use the value of R from circuit B and the equation. What's the value of R from circuit B? Don't forget that this is circuit B. And when the students use this circuit B, the value of resistance he got was, for circuit B, the value of resistance he got was 13 ohms. And that's what we are using, 13. So you go back to the equation given to us, we insert 13. Okay, so R is 13, so we have 13 divided by 1.5. Divide 13 by 1.5, you get 8.7 ohms. Same thing again. All right, let's go to the last one. The third one, calculate a resistance RC. Use the value of R from circuit C and the equation RC equals to 3R. So let's go to equation, the value of R from circuit 3. Circuit 3, the value of R from circuit 3 was 3.0 ohms. So when you went down here to use the value of R as 3, insert the value of R here, 3R. That is 3 multiplied by 3.0. You get 9.0 ohms. Don't forget, you should put your SI unit. Now let's proceed. All of this is just 1 mark. But that doesn't mean you should miss any of this. You miss any one, you miss all the marks. Incident suggests that RA, RB, and RB should be equal. State whether your results support this suggestion. Justify your statement with reference to values from your result. Anyway, if you look at these values, they are close enough. Okay, 8.7, 8.7, 9.0. These are very close values. Okay, if you look at the gap between them, the gap between them is just 0.3. Okay, yeah. The gap between them is just 0.3 out of 8.7, or if you choose to use 9. So what fraction of 9 is 0.3? That is um, that is probably 3%. Okay, so our values are accurate enough. Okay, so yes, the difference between the values is within the limits of experimental error because the deviation is very small. Okay, yeah, that's it. All right, the next one, a student investigates the resistors in circuit A using a variable resistor. To change the current in the circuit. In the space below, draw the symbol for a variable resistor. This is the symbol for a variable resistor. Okay, good. Um, yeah, so we've drawn the symbol for a variable resistor, and then we have an arrow. That's it. Next question. So just one advantage of using a variable resistor to change the current in the circuit. Now look at the circuit we produced. Let me just bring this in. So if you look at the circuit we produced, let me just bring in this simulation platform. So if you look at this circuit, okay, there are three resistors in series, right? Good. And there's current flowing in this resistor. Let me click on schematic. So you see the symbol, this is the cell. There are three resistors in series, ammeter, fine, voltmeter. But if you want to rearrange this circuit and connect it as three resistors in parallel, I have to start disconnecting the resistors one after the other and trying to position three of them in parallel. Okay, so this is how you modify a circuit. You have the original circuit and then you start disconnecting, okay, and then you start bringing in your connecting wires and then bringing in other wires to ensure the circuit works. For simplicity, let me just put this way. So this is how you connect a circuit, and you want to connect resistors in parallel. So this is how you are making the adjustments to ensure everything works perfectly. But what could you have done instead of adjusting the connection of the circuit in order to modify the resistance in the circuit? What could you have done better? What you could have done is instead of rearranging the circuit at every point in time, what you can just do is just put a variable resistor, okay? So when you put a variable resistor in the circuit, instead of rearranging the circuit, remember when I wanted to connect in parallel, I had to disconnect this entire circuit that I did and arrange the three resistors in parallel. But let's assume these resistors were not there and we replace all these resistors with just one variable resistor. All we have to do is to increase the resistance by turning the knob of the variable resistor to the right, or we reduce the resistance by turning the knob of the variable resistor to the left. That's all. So we don't have to disconnect the circuit for every modification we do to the circuit, and that's it. Okay, that's the advantage of using a variable resistor. You do not need to disconnect the resistors and reconnect the circuit again after each reading. That's the end of question number 2. Now we go straight to question number 3. A student determines the focal length of a converging lens by two methods. We have an illuminated object, we have the plain white screen, there's a bench here, and we have a lens here. The students set up the apparatus as shown in figure 3.1. So just one precaution that must be taken when setting up the apparatus to ensure accurate measurements. What precaution would you take? You view the meter ruler perpendicularly, okay? This way you are avoiding parallax error. Just one is enough, okay? And if you do not remember something like this, then you can just talk about the lens, focus on the lens. The lens must be perfectly vertical, okay? The lens must be in a vertical orientation. Let's go to the next question. So the next question says, the student set the distance u between the illuminated object and the lens to 20 centimeters. What's next? He places the screen near the lens and moves the screen until a sharp image of the illuminated object is seen on the screen. Describe a technique for describe a technique for obtaining an image that is sharp. as possible. Okay, describe a technique for obtaining an image that is as sharp as possible. So what is happening here? I'll use this for this demonstration. Okay, so this is the illuminated object, this is the lens, the image will be formed at the other end. So when I move my illuminated object to this 20 centimeters mark, for instance, the reason why I'm saying this here is because I'm using arrows, okay? But in the practical, in the laboratory, in a practical setting, you have an illuminated object that's giving off rays of light, okay? So if I bring this illuminated object to this point here, and in a practical setting, you won't actually see this line that shows rays of light, okay? So I will remove this line completely. I will click on none. So let's assume I bring my illuminated object to this 20 cm mark. How do I get the position of the image? Now, I'll begin to shift the screen forward and backward until it gives me a sharp image. You see how blurred the image is. So I keep moving it forward and backward till it gives me a sharp image. So when I have a sharp image, that is when, look at this center here, look at the center here. That shows us the image, okay? The image is blurred here, image gets sharper, okay, then image becomes blurred again. So when you don't see anything in that center, okay, so it's very likely our image is here. The image is sharp, it is tiny, that's why we can't see it. It's so tiny. If you come here and click on rays of light, you see that rays of light actually meet here. How did I get this point? By moving my screen forward and backward, okay? So if I leave that place, so by moving my screen forward and backward until I eventually got the position of the position where the image is sharp. So that's what we do here, okay? So by moving the screen forward, okay, towards the lens and away from it until a sharp image is seen on the screen. That is how you get your image being as sharp as possible. Measure V1, the distance from the lens to the screen. How do you measure the distance from the lens to the screen? Just put your meter rule here and take measurement of this distance. That's all. So when you take measurement of that distance, what will you get? You get, let's see, 8.1 cm, yeah. So if you use your meter rule here, you get 8.1 centimeters, okay? So I did that with my printed copy because I can't do that on the screen. Now, look at this. Figure 3.1 is drawn to 1/10 scale. That means what you see here is 1/10 of the actual value. Now they are asking you, calculate V1, the actual distance from the lens to the screen. If this is what you have and it is 1/10 of the actual value, what will be the actual value? Just multiply this by 10, you get 81 centimeters. Okay, yeah, to two singular figure, 81 centimeters. Excellent. Let's go. Now, this is the time you start doing your work. The shapes of the illuminated objects and the image seen on the screen are shown full size in figure 3.2. This is the image and this is the object. What are you to do with this information? You are to take measurements. Measure h subscript 0, which is the height of the illuminated object as shown in figure 3.2. Measure this height. When you use your meter rule, you get 1.2 centimeters. Next thing, measure h1, the height of the image on the screen as shown in figure 3.3. When you use your meter rule to take measurement of this height, you get 4.8 centimeters. Though there might be little deviation depending on the accuracy of the meter rule you are using and mine. Good. So now you have to calculate the value m of for the magnification using the equation h subscript I over h subscript 0, which is height of image over height of object. What's height of image? 4.8. So we substitute 4.8 over, what's the height of object? Height of object is 1.2. So if you do 4.8 over 1.2, you get 4.0. This height is given in centimeters, denominator is given in centimeters, they cancel out. That's why magnification does not have any SI unit. So you don't put any SI unit in front of magnification. Now the next question. Calculate a value f1 for the focal length of the lens. Use your values from BII. Use your values from BII. No, this is C. Use your values from BII and CII and the equation F equals to V1 over M plus 1. So let's substitute. What's V1? We calculated V1 as 81 centimeters. Okay, that's the actual value of V1. So we put that here, 81 over M plus 1. M is 4. 4 plus 1, which is 81 over 5. You get 16.2 cm. So that's the calculated value for the focal length of the lens. Okay, the focal length of the lens, we calculated it as 16.2 centimeters. On to question number E. Describe one difficulty that is experienced when using a ruler to measure the height of image in this experiment. So just an improvement to the apparatus to overcome this difficulty. When you are using a meter rule to measure the height of the image, take note that this line was drawn for you, okay, to show how you actually take measurements of height of the image. But in reality, you won't see this line, this vertical line here, you won't see it. You won't see this vertical line. In reality, this is what you see. So how exactly will you successfully get the height of the image when you don't have the line through the center mark, through the center? So you are just the one that will just try to see how you can successfully place a meter rule here. And if your meter rule is not perfectly straight, if it does not pass through exactly the center of the triangle, then you won't get what you're supposed to get. Like this meter rule, for instance, does not pass through the center of the triangle. This is the center of the triangle, and this is where the meter rule is passing through. So that's one difficulty we might experience, and it will give us wrong value. Imagine placing your meter rule like this, okay, because this horizontal line is not there. This vertical line rather is not there. Imagine placing your meter rule like this, and it gives you a wrong height. This is the distance it will give you, a wrong value. So that's the difficulty you can encounter, difficulty in locating the center of the base of the triangle. And how do you solve that? First of all, you measure the base of the triangle and divide by 2 in order to locate the center of the base. Okay, so our difficulty is in locating the center of the base. So we do all of this in order to locate the center of the base. Once you get the center of the base, then you can calculate the height of the base of the triangle. Now you have work to do. What are you to do? The students adjust the position of the lens so that u equals to 40 centimeters. Now the students adjust the position of the lens so that this distance is 40 centimeters. So probably by moving the object backwards so that this total distance will be 40 centimeters. And if you are moving the object, you readjust position of the object. What happens? Position of the image changes. Okay, so you have to reposition the screen in order to get your image correctly. Okay, let's focus on adjusting. Okay, let's focus on the adjustment the students made. The students adjust the position of the lens so that u equals to 40 centimeters and obtains a new value v2 for the distance between the lens and the screen. This is the new value v2 that the student got. Okay, so the student got a new value of distance between the lens and the screen, which is v2. So what will the student do with this? The student then used it to calculate a second value f2 for the focal length of the lens using the equation f2 equals to uv2 over u plus v2. Now let's substitute. U is 40, v2 is 25.1. Substitute all of this into this equation, okay? And what will you get? Whether you put this bracket here or you don't put it, it does not matter, okay? So if you solve this, you get a numerical value of 15.4. That's the value you get for F2, 15.4. But the first time when we use distance, when we use the length, okay, when we use the height rather, when we use the height of the object and the image, this is what we got, okay. And when we use V, which is the distances, this is what we got. Let's go on to the next question. The next question asks us, suggest which value of focal length f1 or f2 might be more accurate. Explain your answer. Which value of f will be more accurate? Is it f2 or f1? Now look at this. In order to get f2, what did you use? we use the distances, the length, okay? We use the distance u and we use the distance to the right, which is v. That's how we got F2. But in order to get F1, we were calculating the height of the object. Let's assume we place meter rule here in order to get the height of this object. Can we see it clearly? No, because the object is small. Let's come and get the height of the image. What do we have here? It's so tiny that we can't see it. And if you try to assign a value to it, there will be very large uncertainty. There will be very large error. Okay, there will be very large error when we are using height of the image. F2 might be more accurate because it is calculated using the distances of the image. Okay, when you use distance of the image, which is large distance in comparison with height, then you get very accurate value. Let's continue. And the object which can be measured. Okay, so F2 might be more accurate because it is calculated using the distances of the image and the object, which can be measured to higher degrees of accuracy than the height of image and object. Okay, F1 was calculated using the height, while F2 was calculated using distances. So the one calculated using distances is more accurate because the distance can be read to higher degree of accuracy, unlike the height that cannot be read to higher degree of accuracy. See how tiny the height of the image is. You can't even get accurate measurement with this meter rule because the image is so tiny that you can't get very accurate readings of the height of the image. So that's the problem with using the height of image to get to calculate the focal length. Okay. So which cannot be measured to higher degree of accuracy, which cannot be measured to higher degree of accuracy. All right, let's proceed. Now we go straight to question number 4. A student investigates the effects of insulation on the cooling of a liquid. Plan an experiment which will enable her to investigate how changing the thickness of insulation surrounding the beaker affect the rate of cooling. How thickness affects the rate of cooling. That's the question. Okay. See, question number 4. Planning. When it comes to planning, if you don't understand this question, this statement, you will continue to move in circles without successfully getting to a final destination. But once you understand this question, this statement of the question, you can just go straight and then completely answer the question and you get your full mark. So now that we understand that we are trying to get the effect of thickness on cooling rate, now we can answer the question. What are the apparatus you have? You have a glass beaker, supply of hot water, a lid to feed the beaker, okay, and strips of insulation which can be cut to size. In your plan, you should list any additional apparatus. Cooling rate. How do you get cooling rate? You measure what? Temperature. What instrument do you use to measure temperature? Thermometer. So this place that says list additional apparatus, we need thermometer. How do you even measure the thickness? We need a meter rule or vernier caliper. These are additional instruments, okay? These are additional instruments. So it's very important you understand what you are doing clearly before you proceed. This is the best video on paper 6 you can find ever. Kindly share it with your friends if you want them to pass. Let's proceed. Okay, so that is noted clearly, and let's go ahead with the answer. Okay, so list any additional apparatus. Additional apparatus are meter rule or vernier caliper and a thermometer. That's all. So by providing answers to this bullet point here, you are answering the question. The next one, explain briefly how to do the experiment, including measurements to take so that the rate of cooling can be determined. How do you explain briefly? Explain briefly does not mean you list what you see on the marking guide. Okay, the way you see it on the marking guide, just list it like that. No, try to be explanatory. Explain the procedure, but go straight to the main point. Don't give unnecessary information like you put water in a beaker, you put it on the heater in order to increase its temperature. You ensure you are gradually increasing the heating rate. We don't need that. Just go straight to you are pouring hot water at 100 degrees Celsius. Okay, so avoid unnecessary information. Go straight to the point. Okay, but don't omit or leave behind any important information, because you don't know the particular information they need from you. If they need you to make mention of certain things, like the number of times you are repeating the experiment and you don't mention it, you might not get the total number of marks, though there are always other point you can put to get your marks fully. All right, let's go straight with to the way I answer the question using the bullet point. The next bullet point says, explain briefly how to do the experiment, including measurements to take so that the rate of cooling can be determined. So what did I do? Okay, I drew a diagram, though you may draw diagram if it helps explain your plan. Okay, the diagram is not necessary. I chose to draw a diagram. So I draw my diagram. Okay, I put the water, I put the insulation around the beaker. I label even the glass beaker itself, the thermometer. I did not label the meter ruler or vernier caliper. I didn't bother drawing it, because it's not part of the setup when you are heating, when you are measuring the rate of cooling. Okay, you use the meter rule or vernier caliper before you set up this entire setup. Use it to measure the thickness before you use it to wrap this beaker. So let's proceed. Pour 200 cm cube of water at 100 degrees Celsius into a beaker, wrap with 1 cm thick insulating material. So after pouring the water into the beaker, what's the next thing? Wait for the temperature of the water to become 90 degrees Celsius. So we wait for everything to attain one uniform temperature, and then we start a timer. Now you start your experiment. You start taking readings. What are you reading? Read the final temperature of water after 5 minutes. So let us see what the final temperature will be after 5 minutes. If the cooling rate is high, the final temperature will be low after 5 minutes. But if the cooling rate is low, the final temperature will be high after 5 minutes. So the magnitude, the value of the final temperature would help us to predict what the cooling rate is. Okay, so let's see. Read the final temperature of water after 5 minutes. Then you repeat the procedure with an insulation of either of these thickness. Okay, so we use an insulation that has a thickness of 2 mm or 3 mm or 4 mm or 5 mm thick. Okay, so we use any of those insulators to wrap the beaker in each case. After that, you record the final temperature and the thickness of the insulator in the table below. So this is the table: thickness of insulator, final temperature. That's it. This is the table. What else are we supposed to do? State key variables to keep constant. This is where I listed the variables to keep constant. The initial temperature of water and the size of the beaker must be kept constant throughout the experiment. Also, view the thermometer perpendicularly in order to avoid parallax error. The question does not ask us to state this, but it is wise to state at least one safety precaution in case the math scheme wants that. Don't forget, it is part of your procedure. Safety precaution is also part of your procedure. So there is no harm in just adding one step to take to ensure you get accurate readings. Okay, so that's it. Avoid unnecessary information, but give them all the important points you know. Give them all the important points you know. Okay, once you do that, you get all the marks. After all, it's just 7 marks, so you get all your 7 marks. What's the next thing? Draw a table or tables with column headings to show how to display the readings. You are not required to enter any readings in the table. So you draw your table, and this is my table, and I've included the column headings. These are the column headings. I didn't include any value. You don't need to enter any numerical value. What's the last thing? Explain how to use the readings to reach a conclusion. How you use your readings to reach a conclusion? Just tell us that plot a graph of final temperature against the thickness of the insulator and calculate the slope of the graph. That's all. Or you tell us you look at the trends on the thickness of insulator coulomb and final temperature coulomb, and whichever thickness that gives you the lowest final temperature has the highest rate of cooling. You get it? Yes. So this is one way of answering this question. Don't forget that in this case, we are checking the we are checking what? We are checking the final temperature after 5 minutes. So you may choose to have a fixed value of time. Use 5 minutes for all the experiments and check the final temperature after 5 minutes. And you may choose to do this experiment another way, okay, by checking the time taken for the experimental setup to reach a final temperature of, let's say, 30 degrees Celsius. So if the cooling rate is high, then it will take a very short period of time to reach this final temperature. But if the cooling rate is low, that means it cools slowly and it will take a very long period of time to reach this final temperature. So I've also stated this there, I've also answered this here, okay, an alternative way of answering this question, okay, an alternative way of answering question number 4. I've answered it here, all the steps you have to take. What will you do? Pour 200 cm cube of water at 100 degrees Celsius into a beaker, wrap with 1 cm thick, okay, I use cm here. 1 cm is a large value for thickness when it comes to experiments involving insulation. A more reasonable value to use would be in millimeter, okay? Yeah, a more reasonable value to use would be thickness in millimeter. So I've changed that to millimeter, small letter m. So that would be a better reading to use. All right, so wrap with 1 millimeter thick insulating material. Wait for temperature of the water to become 90 degrees Celsius and start a timer. Now, what will you do with the timer? Read the time taken for the final temperature of water to become 30 degrees Celsius. So in this case, we are using time. Determine the time taken for each thickness of insulation. So once you do this, you also get your correct answer. So there's no particular way of answering question number 4. It's planning. You bring your creativity into play. Let's go on. Repeat the procedure using one of 2 millimeter, 3 millimeter, 4 millimeter, and 5 millimeter thick insulator. So wrap the beaker. In each case, record the time taken and the thickness of the insulator in the table below. So, and then you do the rest, recording thickness of insulator, then time taken to cool, okay, or time taken to reach 30 degrees Celsius. That's all. What else are we to do? You have to state the values you keep constant, okay? State key variables you keep constant, okay? And what are the variables you keep constant? Initial temperature of water, size of the beaker must be kept constant throughout the experiment. You get it? Good. Also, since we want all of them to reach the final temperature of 30 degrees Celsius, you can also add that to your variables to keep constant. Okay, use a final temperature of 30 degrees Celsius for all sample. Okay, for each reading of your experiment. That's it. Then we view the thermometer perpendicularly to avoid parallax errors. You can just add one step you take to ensure you avoid errors. Then what else? The final thing, you plot a graph of time taken against the thickness of insulator and calculate the gradient of the graph or slope of the graph. That's all. Thank you very much for joining us. That gives you how to answer question number 4, practical question. Make sure you go through this video and understand every step taken and everything we've done. Once you do this correctly, you make excellent grades in your examination. I remain Adeboale Jimo, Physics for Everybody. Ensure you subscribe to this channel and continue to invite your friends to watch my videos. See you next time. Do have a nice day. Goodbye.